Hi, it is my pleasure to introduce STeLLAR, an open source framework that clears the serverless clouds, shedding the light on their performance. What keeps the cloud users awake at night? Actually, just two thoughts. First is how to manage the cloud infrastructure that their services use and avoid any trouble, and the second is whether their services are fast enough to keep their clients happy. Good news, the new programming paradigm, called Serverless, frees cloud users from the first headache completely. Serverless clouds allow cloud users to focus on writing their code as a composition of functions, whereas the cloud providers take care of function deployment and automatic scaling of function instances according to traffic changes. This labor division boosts developers' productivity, allowing fast time to market for their products. Okay, so cloud providers have eliminated the first headache. This talk seeks to eliminate the second haunting thought. In reality, the new programming paradigm, serverless, raises a lot of non-trivial questions. First, let's think from the cloud user's perspective. If cloud infrastructure is an entirely provider's job, as cloud users, we would like to choose the provider that does the best in the fastest and the cheapest way. Second, how do we compare different providers? Their infrastructure literally has 0 software components that would be the same in different clouds. And finally, if we decide to port an application to serverless, how can we reason about its performance? In fact, we barely know which factors impact its performance. And even if we have a professional doing the porting, what if we decide to change the providers in future? These are all good questions, but the main question is, what is inside the serverless cloud? But serverless clouds are obscure, keeping their components hidden from the cloud users. And that is why we introduced STeLLAR, the serverless state latency analyzer. STeLLAR is our open source and provider agnostic framework, which supports AWS Lambda, Azure Functions, and Google Cloud Functions as of now. STeLLAR offers an end-to-end and in-depth performance analysis framework that is configured to explore the latency and do the root cause analysis of proprietary clouds. Next, we will showcase STeLLAR by evaluating and comparing the leading providers, but before that, let's briefly talk about the internals of the serverless platforms and the intuition behind the STeLLAR's design. At a high level, the serverless infrastructure has two goals: scaling cloud resources in the form of function instances based on changes in function invocation traffic. And second is, these instances should be able to run on any node in a data center in the whole server fleet, allowing the providers to keep their servers highly utilized while keeping the cost of serverless computing low. Our key observation is that serverless clouds feature the following fundamental components, all of them, namely the cluster scheduler that is on the way of all incoming invocations, selecting or spawning the appropriate instance for each function invocation if necessary. The lead of the worker nodes where function instances can run, and the storage that holds the initialization state. For example, container images for spawning new instances of functions. The same storage service is used for transferring data across functions because they are stateless and cannot hold state. With this insight, we can now assess the performance of clouds by stressing their key components. To stress each of these components separately, we configure the following parameters. One can stress the worker nodes by changing the characteristics of the deployed functions. STeLLAR can trigger warm function invocations if it invokes functions frequently, for example every second, so that the providers keep function instances for this function alive. Or trigger cold invocations, invoking functions rarely, for example once in 30 minutes, which causes spawning a new function instance before an invocation can be processed, which is called a cold start. The time it takes to spawn a new instance highly depends on the function characteristics that STeLLAR can vary as well. For example, STeLLAR allows to use two deployment methods, namely deploying a function with a zip archive or a container image. Also, STeLLAR allows to choose a language runtime, for example, deploying a function written in Python or a function written in Go. Then, one can stress the storage service with the following parameters. First, one can vary the size of the function image, which is the necessary initialization state of a function. A function image size is configured by adding a random content file to the zip or container image upon function deployment. Second, one can deploy a producer function that invokes another consumer function while transferring a random content payload of a configurable size. Finally, to stress the scheduler, STeLLAR steers function invocation traffic of a configurable shape. For example, STeLLAR can invoke a function once at a time, or alternatively, issue bursts of several invocations at once to the same function. Second, STeLLAR specifies whether a function should return immediately or execute for some time, which is modeled by busy spinning in the user code. Now, let us consider the design of the STeLLAR framework. STeLLAR is provider agnostic by design. The key insight behind the STeLLAR's design is that the deployment interface is different for each provider, but the invocation API is just the same URL or HTTP-based API for any of the providers. Hence, we introduce a separation between the deployer logic, which automates function deployment, and the client, which drives the load and performs the measurements. Using a static configuration file, the deployer automatically configures and deploys the requested set of functions, producing a file with the corresponding set of endpoint URLs, one for each of the deployed functions. After deploying the functions, one can run the STeLLAR client, which drives the load to these functions and measures their response time. In our experiments, we studied the distribution of the collected response times and measured the median and tail latencies in particular, where the tail is the 99th percentile. As a metric of variability, we use tail latency to median latency ratio, or tail to median ratio. So now, let us discuss the evaluation methodology in detail. First, we set up the STeLLAR client on a node in the Uther Cloud Lab data center. We then deploy the serverless functions in data centers located in the western coast of the US, close to where the STeLLAR client is deployed. To guarantee that the function instance would have a full CPU core quota, we configure the functions to have the maximum memory sizes of 2 GB for AWS and Google and 1.5 GB for Azure. We deploy all functions using the zip-based deployment method, which is supported by all studied providers except one experiment in AWS, where we evaluate the performance implications of the zip-based and container-based deployment methods to compare them. We deploy Python 3 functions for all experiments except the function image size and the data transfer experiments. In those experiments, we use Golang functions to minimize the image size for the baseline and also maximize the accuracy of the measurements with the user code timestamps for the data transfer experiments. First, we evaluate the response time of warm and cold functions by steering invocations to these functions one at a time, with one outstanding invocation at a time to each function, with a different inter-arrival time. Invoking functions frequently, for example once per second, results in warm starts, whereas invoking them once in 30 minutes causes cold starts, where a function instance needs to be spawned before processing the invocation. These charts show latency CDFs on the y-axis and the latency in milliseconds on the x-axis, with warm invocations on the left, cold on the right. Note that x-axis limits on the two charts are different because cold invocations are much slower than warm. One can see that warm invocations are much faster than their cold counterparts. However, in both cases, latency variability, tail to median ratio, is quite moderate. We now assess the code function delays in AWS that appear on worker nodes with different language runtime choice and while using different deployment methods. The chart shows the latency CDFs just like before. Runtime languages are shown in different colors. Solid lines stand for zip deployment and dashed lines stand for container-based deployments. One can notice that Python container deployments are significantly slower and more unpredictable than all others. One possible explanation of this phenomenon is that a Golang program is compiled as a single static binary, suggesting that both zip and container image comprise the same binaries that are likely to be stored in the same storage service. Meanwhile, for Python, a container-based deployment shows higher median and tail latency compared to the corresponding zip deployment. We think that this is because Python imports modules dynamically, requiring on-demand accesses to multiple distinct files in the function image. When combined with a container-based deployment method, we hypothesize that this results in multiple accesses to their underlying storage with the function image. Because in AWS, containers support splintering and on-demand loading of image chunks. The additional accesses to the image store would explain the high cold start time and latency variability for Python container-based deployments. So we see that the combination of the runtime choice and the deployment method can impact performance. Compared to Zip's, container-based deployment for Python significantly increases both median and tail latencies. In this experiment, we assess the impact of the image size on the median and tail response times upon a cold start by adding an extra random content file to each image. We only consider zip-based deployment method here, as this method is supported by all three of the studied providers. On this chart, you can see a set of CDFs for different providers and image sizes. Providers are shown with different colors, and the image sizes are shown with solid, dashed, and dotted lines. The image size here means that, for example, image size of 1 megabyte means that a file of 1 megabyte in size was added to the image. And 100 megabyte means that a 100 megabyte file was added to the image. AWS shows considerable sensitivity to the image size. Increasing the added file size from 10 to 100 megabytes results in 3 to 4 times increase in the median and the tail latency. Azure exhibits even higher sensitivity to the image size. In contrast, we observe that Google is not sensitive to the image size, with nearly identical CDFs for different image sizes. We believe that this is because our benchmarking functions never touch the added file, which allows Google to skip this file's retrieval from the storage and optimize the latency. Invocations of cold functions may impose large delays of up to several seconds to the median response time, particularly for functions that have large images. However, variability of the cold starts is moderate, with tail to median ratio of less than 4 for all providers. Next, we study the data communication delays for an application of two functions, where one function transmits a payload of a configurable size to the second function. Since functions are stateless, data is transmitted via a storage service, with the first function saving a payload to storage and the second function loading the payload from storage. We capture these latencies with timestamps taken by the user code in these functions. The invocations are triggered frequently, making sure that no cold starts are observed. On the left chart, one can see the median latency, shown with solid lines, and the tail latencies, shown with dashed lines. On the right chart, the CDF lines for 1 megabyte and for 1 gigabyte payload transfers, respectively. Clearly, storage transfers are slow and have very unpredictable response time. For example, for 1 megabyte transfer in Google, these delays result in mere 150 millisecond median and 6 seconds of tail latency, yielding a tail to median ratio of nearly 40. We now investigate the behavior of serverless clouds in the presence of bursty function invocations, varying the number of invocations in a burst. We notice an overall increase in latency as the burst size increases, which is most pronounced for Azure compared to Google and AWS. Moreover, we notice that for AWS, the response time actually decreases with large burst sizes, which is counterintuitive. We believe that this phenomenon is due to an internal optimization where the cold start of the first invocation speeds up the cold starts of the other invocations in the same burst. Despite the increased latencies with large burst sizes, all providers show moderate latency variability with tail to median ratio less than 3. We studied the response time of functions in the presence of a bursty traffic with long function execution times of 1 second to assess the queuing effects across concurrent invocations of the same function. We find that the choice of the scheduling policy dramatically impacts function response time. In this chart, solid lines represent CDFs obtained by sending individual requests, and the dashed lines plot the CDFs for the invocations that come in bursts of 100 invocations. From the chart, it becomes clear that all three providers have different policies. AWS has little sensitivity to the burst size, meaning that AWS policy demands spawning a new instance on every invocation in a batch of concurrently arriving invocations. In contrast, Google and Azure show a significant increase in the median and tail latency for the bursty traffic compared to serving individual invocations. Hence, the choice of the scheduling policy and its efficiency is crucial for a serverless system. Reasoning about performance of applications running in serverless clouds is difficult, and this is because the cloud infrastructure is obscure to cloud users. Our work introduces STeLLAR, an open-source serverless benchmarking framework that enables performance and even tail latency analysis of serverless clouds without an access to their proprietary components. Our analysis identifies that modern serverless clouds have the same fundamentally required components, namely the scheduler, the storage service, and the worker node fleet. Out of the three, the storage and the scheduler are the key performance bottlenecks across all of the three leading providers that we benchmarked. STeLLAR clears the serverless clouds. Check our framework online and join the community on GitHub. Thank you.